Okay, so let's continue our lessons on magnetism. Okay, right. So this is the topic of magnetism. Okay, in which we learned this topic last week. Okay, so we will continue this topic in a sense of the continuity of from the last week, which is we stopped at the force of the magnetism. So let's do some recap. So this is the learning outcomes, okay, of the topics, and this is the units of chapter of the magnetisms, okay, and of course we start at the magnetic field, right? So what is the magnetic fields, right? So it's actually based on field. It's actually in Malay we call it as medan. Okay, medan magnet. Okay, so the magnetic field is the when you have a permanent bar magnets. Okay, so definitely the permanent bar magnets will have its poles. Okay, and opposite poles. Okay, is called north and south. Okay, kutub utara and kutub selatan magnet. Okay, and like poles will repel and opposites will attract. Okay, same goes to charge. Okay, charge positive meets with charge negative, it will attract, and if the charge positive meets or charge positive, it will oppose. Okay, if a magnet is broken in half, okay, each half has two poles. Okay, meaning that okay, it's very easy to understand. It's either if we have one magnets that have only one south pole and one north poles at the end and at the edge of the magnet. But if you try to break the magnet, then what happens is okay, you still can have a, a sets of north and south. Okay, regardless of the where it's broken, and it still can have south and north poles. Okay, and the magnetic field lines is like this. Okay, and when you look at the top figures on your right hand side, okay, you can see that the magnets are filled up with the is full with the iron fillings. Okay, the iron fillings, and we can see that at the end, at the edge of the magnets, okay, we can see that all the iron fillings is probably gonna is either going out or coming into the magnets. So we cannot say from here we cannot say that iron filling is going into or it's coming out from the edge. And but we can easily understand that there is a point where all the magnetic field lines comes and goes. Okay, so same goes to the U. Okay, if you look at the this is the permanent bar magnets, and now we have U. Okay, magnets in the shape of U. So we can see here there are at the end or at the edge of the magnet, we can see that all iron fillings will go will go. It's going to or going out, right? But in the sense of if you want to know which direction is the magnetic field lines, then we should use a compass. Okay, what is compass here? The directions of the magnetic field at a given location is the direction in which the north pole of a compass points when placed at the locations. Okay, so when you have a compass, so normally when you have a compass, you can see that there is a red arrows. Okay, the red arrows is actually pointing into the north. Okay, we always say that compass is always pointing north, especially for the red arrows. Okay, the red arrows is always pointing north, and we can say that. Okay, uh, when you put a lot of compass around the magnet, you can look at the arrow is actually coming out. Okay, coming out from the north pole of the magnets and will be going into the south pole of the magnet. So in here we can see that okay, it's go like this. Okay, coming out from the north pole. So this is your north pole, right? So the magnetic field lines will goes out from the magnets from the north pole and will be going and will be coming, and we put another compass here. So you can see, look at the directions of the red arrows. It will be pointing. And we can see that the pattern is actually going out from the North Pole and will be going into the South Pole. You can put a lot of compass and you can see that the compass will be do like this, and it will be pointing into the south poles of the magnet. So that is how the magnetic fields lines of the magnet. Okay, but please remember that the magnetic field lines comes from the north pole into the south poles. Okay. And this is the geomagnetism. Sometimes they will ask you in terms of what is your understanding in terms of geomagnetism. Okay, what is your understanding in terms of what is the geomagnetism is all about. Okay, so it's actually based on the two versions of how can we interpret. Right, okay, because we always say that the north geographic pole, okay, north geographic pole is a kutub utara. Okay, North Pole, kutub utara. Or should we say Arctic? Okay, Arctic. And at the bottom we have Antarctica. Okay, Arctic at the North Geographic Pole, and this should be your South geographic pole. How do I know geographically? Yes, based on atlas. At the top of the atlas or at the top of the globe is called North. And at the bottom of the pole is actually South geographic pole. So when you have a compass, okay, when you have a compass, like I've said just now, the compass, the magnetic field line is actually pointing, okay, on our understanding, okay, that lines is actually pointing, sorry, the red arrow is actually pointing to the north, okay, but according to the south pole of the magnet, it's not going to the north. Instead, it's going to the south. Okay, look at this. Okay, try to imagine that this is your globe. Okay, all right. So we can see that the red arrow is actually pointing to the south pole of the magnet, not the north pole. Okay, south pole of the magnet. So we can conclude that the north geographically pole is actually the south pole of the magnet. Okay, south pole. So this part is actually south pole of magnet. Let's say if you try to imagine that, okay, we have a big magnet inside our earth. Okay, so that is south pole of the magnet. So is equivalent to the north geographic pole. The north geographical pole, because of its location. Location is at the top of the globe, so we can say that is the north geographic pole. But according to our understanding, in the sense of magnetic field lines, okay, the magnetic is always the compass will always show that it will be pointing into the south. So make it very clear that at the Arctic, okay, as we said, this is Arctic, okay, Arctic. Okay, we have there is a north geographic pole. Okay, in terms of geographically, it should be north, and but at that point is actually south pole of the magnet. Okay, remember two terms. Okay, north geographic, south pole of a magnet. Magnet akan jadi south. Okay, but in the Antarctica, okay, so we have a south geographic pole because its location is at the south, but in terms of magnetic, it should be north. Okay, north magnetic pole. Okay, so that is the word called as geomagnetism. So that is quite different between south pole of the magnet and also the north pole of the geographic. Okay. So now we bring to this part the magnetic force on a moving charge. So this is the magnitude of the magnetic force. Okay, so remember, okay, now we learn about moving charge. Okay, moving charge, where you should understand that charge comes from the positive or negative charge. Right? So positive and also negative charge. So we want to know what is the magnitude of the magnetic force. Okay, magnetic force. Okay, don't care about the word magnetic, but we should learn this thing. force. So force means that the unit should be Newton. Okay, so that's why the F is equivalent to QVB. Okay, QVB sine theta. How they got that? They got the sine theta. Okay, I'll explain to you later. But this is due to this is charge. Q is charge, magnitude of charge. Okay, so that's why Q is in the modulus. Okay, regardless of the negative or positive, the answer should be all positive. Okay, the same goes to what we learned in the electrical part. Okay, electric field is always positive, electric force is always positive. If we have positive or negative, it's just due to the directions. Okay, and how about V? V is the velocity of the charge. You know that the charge will move, okay, with a certain velocity, so there is a velocity. And how about B? B is the magnetic field. Okay, now we have F equals to QVB sine theta. F is the magnetic force. Q is the magnitude of charge. V is the velocity. While ball, volleyball is the magnetic fields. And how about sine theta? Sine theta is the angle between velocity and magnetic field. So here are the some of the reference. How can you decide what is your delta theta? Okay, so look at this first part. Okay, let's say this is the first part where you have this is the first part where you have a positive charge that going, okay, into the magnetic fields, but perpendicular to the magnetic fields. Okay, so the charge is perpendicular to the magnetic field. So the positive charge is going down while the magnetic field is going to your right. So what happened is the theta here is 90. Okay, if you put 90 inside the equations, then you can have sine 90 F equals to QV sine 90. Remember, sine 90 is equivalent to 1. So we can have QVB. So this is what we call F max, maximum force. Okay, so what happens if we have a second situation where the magnetic field, the velocity and the magnetic field is parallel? What happens if the magnetic field and velocity is parallel? So theta here will be 0. So when theta 0, F equals to QV B sine 0. So sine 0 is what? 0. So if 0, then your force field should be 0. Okay, so this is the 0 force. Okay, and then if we have a theta, so let's say the theta here, then this is where you get QV B sine theta. So remember, okay, we can either use F equals to QVB if the situation is theta equals to 90. But if the theta equals to theta, then you should use the equation QVB sine theta. While if the theta is 0, meaning that the velocity and the magnetic field is parallel, then the theta should be 0. Okay. So the magnetic force on a moving charge is actually used to define the magnetic field. So in a way, okay, we have to have F equals to Q V B sine theta. Okay, or normally we put that as F equals to Q V B, right? If the theta is maximum, if the theta is 90 or F is maximum, then we can rearrange the equation so that we will try to define what is the magnetic field in the sense of equations. So in this case, we have B equals to F over QV sine theta, or F equals to F divided by QV. Remember, V is not electric potential, okay? This is never going to the electric potential, but V is velocity. The unit of V is meter per second. Okay, meter per second, right? So in a way, all the values, okay, is if I'm saying the force is actually have a SI unit of Newton. Okay, Newton. but the B magnetic field is based on this part, which is Tesla. The easiest way to say this is Tesla. SI unit for the magnetic field is Tesla. Okay, or uh, Newton per AM. Newton per AM. So it's quite complicated to say this word. Just use Tesla. Okay, magnetic field. Okay, if you use the SI unit, the correct SI unit for F, Q, and V, so we can easily get the Tesla. Okay, remember to use SI unit. Okay, so force is actually force and magnetic field share the same thing, which is both are the vector quantity. Both are vector quantity. So when you have a vector quantity, so normally we can have magnitude, and of course we may have directions. So from magnitude we can easily calculate from the equation, but how to get the directions? Okay, so for put that thought first, then we should learn back how can we discuss or how can we solve the problem using these examples. Okay, so particle 1, okay, with a charge q1 equivalent to 3.6 microcoulomb and a speed of v1 equals to 862 meter per second. So all are in the SI unit. Okay, look at the unit first. Okay, the travels at the right angles to a uniform magnetic field. So this one theta equals to 90. The magnetic force it experienced is 4.525 10 power of negative 3 Newton. Okay, now we have one situation, and another situation is particle 2 with a charge q2 and a speed blah 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 move at an angle of 55 degrees. So this one theta equals to 55 degree relative to the same magnetic field. So find it the strength of the magnetic field. So first of all, you need to define what is the magnetic field at point A. Okay, at point particle 1. So now what we should do is we can use B F equals to QVB sine theta. Okay, QVB sine theta. So we rearrange to get B. Okay, because we have already F, so F over QV sine theta. Remember, at the first part, theta is 90. So theta is 90, sine 90 equals to 1. So therefore, we can have F equals to QV. So what is F? 4.25 10 power of negative 3 divided with Q. How many Q? 3.6 10 power of negative 6 times with the V. It's 862. And this answer is it's not stated here, but the answer is 1.37 Tesla. Okay, 1.37 Tesla. T, capital T. Okay, Tesla is capital T. Okay, and for the second part, the magnitude of the magnetic force exerted on the particle. So remember, if we are using magnetic fields, okay, magnetic fields, and both charges falls on the same magnetic field, we can use that the answer from part A in part B because they use the same magnetic field. So that's why the question is connected to each other. So therefore, magnetic field is equivalent to 1.37. Then we should use 1.37 Tesla into the same magnetic the same question of part B. Okay, so the part B wants you to show to give the value the magnitude of magnetic force. So F is equivalent to QVB, but this time sine 55. Okay, so you do sine 55, right? So use the same Q because it comes from not the same Q, 53. 10 power of negative 6. Our B is 1.3, 10 power of 3, and B 1.37, and sign with 55. The answer is 0.0773 Newton. Okay, all right. So the idea is here, they want you to understand that you can use the same magnetic field. And from point A, you calculate the magnetic field first, and then you will use the magnetic field into the part B questions. Okay, so this will, so we don't have to find back all the magnetic field because you can use the same magnetic field as part A. Okay. So basically, like what I'm saying just for you just now, um, we should use, okay, the magnetic force F is the vector quantity. Okay, it's a vector quantity that should have a magnitude and directions. Then the magnitude is given by, okay, equation UVB sine theta, and direction is we should use right hand rule. So what is right hand rule? Okay, in order to figure out the directions of the force on a moving charge, you can use a right hand rule. So what is right hand rule? So I mean what all of you to look at me. Okay, look at me right now. So please, okay, use your right hand rule, meaning that, okay, your right hand rule should be like this. Okay, your thumb should be the directions of force, and your fingers should be the directions of velocity. Okay, of the velocity. So uh, we should know that the directions of the magnetic fields, okay, of the directions of the magnetic field, that we should go by slapping our hand. Okay, slapping means go front, ke depan. Okay, you cannot go backwards like this. You cannot go backward like this. Okay, but it should always forward, going forward. Okay, dia mesti ke depan sahaja. Okay, so right now, the force will follow whatever the directions of the directions of V and B when you try to get the directions of force. So it should go like this. Okay, F equals to QVB. Okay, look at the equation. F equals to QVB. It comes from F vector equals to Q is not a vector, but V is a vector. Crossing to B is a vector. Okay, V cross B. So how to do V cross B? So first you need to point to the V part. Okay, let's say we try to imagine. Okay, try to imagine we have the system of X, Y, Z. So you in this part you need to understand the system of X, Y, Z. X, Y, Z meaning that the axis of X and Y, Z. Okay, try to remember X is your X. Okay, X, Y is the top and bottom, and Z is to the front and backwards. Okay, okay, I will repeat. Okay, the x-axis is where you go to the left and right. That is x-axis. Especially to the right, to your right is actually positive x, to your left is actually negative x. To the top is actually positive y, and to the bottom is actually negative y. To the front, go to the front is actually your positive z, and to the back, okay, going to the back is actually negative z. Okay, so try to understand that first, which means you have to imagine this thing in 3D, okay, in 3 dimension. X exists, Y exists, and Z exists. Try to master all 3 possible axes. Where is your X? If I say this should be the directions of negative Y, so you know where is negative Y. You should understand what is negative Z. What is the positive X? What is negative X? Now you should know. You should not be able. You should be able to understand all possible locations or all possible directions of X and Y and Z axis. Okay, because our thumb is the directions of force. This is the directions that we want to achieve. So we want to calculate, we want to know what is the direction of force, right? The directions of force is based on whatever happens to the B. So, right, saying that just now, okay, try to put your hand, okay, to the at your screen, whatever screen you are using, either laptop or phone. So try to put like this, okay? Try to do something like try to put your palm, okay, the palm of your hand. Okay, try to imagine that V is going to the x-axis, positive x-axis. Okay, positive x-axis. And then what happened is we want to calculate. Okay, we want to, so V, okay, according to the equation, V must cross B. How to do crossing? Crossing is by slapping. Okay, awak kena cari B. You have to find B. Volleyball kan, volleyball means slap ke depan kan. Awak tak main volleyball pun macam ni kan. Okay, awak main volleyball awak pun, okay, you should tampar bola tu kan ke depan. Ke depan meaning that this is V crossing B. V crossing B. Okay? But all you must use a right hand rule. Okay, right hand rule. Dalam gambar tu nampak macam saya tangan kiri Okay, is actually my right hand. Okay, use your right hand rule. So put your V, okay, put your V to the positive X and try to do slapping, meaning that, okay, try to move your fingers, going to B, going to the magnetic field, okay, which is slightly between, let's say, slightly between positive X and negative Z. Can you imagine that thing? Okay, right. So try to do it that way, that you can see that the direction of force is actually going into the positive Y. Okay, going into the positive Y. Or at the top view, okay, let's say if you're using the top view, look at the top view. So let's say if you have positive X going to your right. So let's say this is positive X. So where is your negative X? Should be here. This is negative X. This is negative X. So to the front is what? Positive Z. And to the at the back of the positive side is negative Z. So this is what I'm saying. So V crossing B, V crossing B is where you go from V to B. This is V to B, and the angle is here. Okay, the angle is there. So we can say from the top view, from the top view, you cannot see where is the positive Y. Okay, you cannot see where is the positive Y because the positive Y is pointing to your eye, pointing to your eye. Okay, the positive Y is pointing to your eye, where the negative Y is actually pointing to the cardboard. Okay, let's say this is your cardboard, right? Then so I'm saying you should try to do it on your own. Okay, positive X, negative X. Okay, positive Z, negative Z. So that's why I'm saying B is actually, okay, in between X and negative Z. Try to imagine X and negative Z. So we can have, well, the directions of F is positive Y. Okay, direction of force is positive Y. Okay, positive Y. Okay, so it's very good to understand that part, right? Okay, so let's look at this part. Okay, this relationship between the three vectors, magnetic field, velocity, and force, can also be written as a vector cross product. So remember, you learned in the previous, not the previous, in the previous semesters, the semesters one, we learned about vector cross product, meaning that to multiply vectors, we have either using vectors or either using vectors or either or scalar quantity. So it's either you have a multiplication Okay, multiplications of vectors either using cross product or dot product. Cross product is going to have a vector quantity, and dot product will have a scalar quantity. Okay, so when you have a vector quantity like this, so V cross, this is a vector cross product. Okay, vector cross product. And V cross B. So try to do it on your own. Okay, so try to imagine this is the where the look at the magnetic field here. The sign of X is meaning that the magnetic field is pointing into the page. Okay, so if you have this sign, so this is pointing out of the page. Okay, so this one is a pointing out of the page, and this one is pointing into the page. Okay, pointing out of the page and pointing into the page. So try to do it on your own. So V cross B, okay, V cross B, okay, V, okay, go into your x-axis, go into your x-axis. Try imagine where is your x-axis, going into B. Okay, B is where? B is into the page. So try to bend your fingers, not thumb, fingers into going into the page. And what happened? Where is your directions of force? It should be going upwards, and upwards in this case is just a positive y. If we use a Cartesian coordinate, I use a Cartesian coordinate because I want to explain to you the directions. Where is that? What is it exactly? Okay, what is exactly the directions of force? But instead of using a Cartesian coordinate x and y and z, you can use also is going upward, going downward, going into the page, going out of the page. So there's a lot of ways to give the directions of force. Okay, directions of force can be write down as using x, y, and z axis, or maybe you can use right, left, top, bottom, going out of the page, going into the page. So it's either that way. Okay, but for the negative part, the negatively charged particles will use the concepts of right hand rule, but using the left hand. Okay, using the left hand. Where is your left hand? Okay, let me explain to you. So this is should be your left hand. Okay, use the left hand. Use your left hand. The fingers should be the directions of velocity, and your thumb is actually force. But for the negative charge, we use left hand. Okay, for the positive charge, we use right hand. Your right hand, not my right hand in the image of that. Okay, so image of okay, negative will use left hand, and positive will use right hand. Okay, right. So this kind of situation is actually the same, okay, the same as where you want to use left hand Fleming. The same goes to left hand Fleming. So the left hand Fleming, okay, let's look at left hand Fleming. Okay, the thumb is actually force, the same. Okay, thumb is actually force, but your middle finger is velocity. Okay, middle finger is velocity, and the point fingers, jari tunjuk, okay, is actually your magnetic field. Okay, it's just a different that way. Okay, for the positive charge, remember, for the positive charge, what I teach you just now is the right hand rule. You should use right hand rules. Okay, for those who have been confused between what to use, left or right hand, okay, try to forget about the left hand Fleming. Just use the right hand. So take up your right hand. Okay, look at your right hand. So all the fingers is the velocity. Okay, and the thumb is actually force. Try to do that way. Okay, don't try to remember what you learned on the form 5. Try forget it. Okay, just concentrate on this one. But for those who have been okay, really okay, use the left hand fleming. Okay, you can use the left hand fleming. Okay, so I want to show you. Okay, this is using my right hand, so this should be my right hand. Okay, right. So right hand. Can everybody see it? So right hand. So this will be your velocity. Okay, velocity, the directions of velocity, and this should be your directions of force. So when you do slapping, when you want to find what is the directions of force, this is where you can get. Okay, so F equals to QVB. V goes to B. V goes to B. V goes to B. Okay, V goes to B, so we can have either way, like this. Okay, okay, like that. It must be okay. The direction, the next directions of the force should be going forward only. It cannot go backward like this. Okay, look, it cannot go here. Cannot go like this. Cannot. Okay, it should go forward, forward only. So we should find ourselves where can we do some arrangements to our fingers, okay, so that we can go to magnetic field afterwards. Okay, from this part. Okay, katakanlah kita nak pergi ke kiri, to your kiri atau ke kanan. Okay, so it's actually you have to find where is B. Kalau B kita duduk di sebelah depan, then okay. So the force is going upwards. Tapi katakanlah dalam kes macam ni, direction sama, tapi B kita kena pergi belah depan sana. Okay, belah ke arah page awak. So F dia akan going ke bawah. Okay, so let's do some. Okay, let's take a while. Try to digest it first. Okay. Right. And the negatively charged by using the left hand. Okay, for those who are using a right hand rule, negative charge, use your left hand rule. Okay, left hand rule meaning the same. Okay, fingers is the velocity and thumb is the magnetic force, directions of magnetic force. Okay. Right. Okay, let me. Okay, I think I'll stop here. Okay, I'll stop here first.